Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about digital systems, so let's get started. Hello everyone, so let's talk about digital systems, shall we? So if I write this word digital down here, right, what do you think of? What are the terms that you think of? I mean, some descriptors you might want to think about are something called discrete, right? Like a discrete value. That's an example of one, right? Discrete, right? What else? Well, a switch is either on or off, so I guess you could think of the word switch. That could be thought of as digital, right? Numbers are pretty discrete, aren't they? When you say, how old are you? Well, I'm 20, I'm 30, I'm 15. However old you think you are, I'm not going to tell you how old I am. That doesn't matter here. But anyway, so digital is one, right? I mean, digital, those are some descriptors for it, right? If you talk about analog here, analog is, well, you can think of it as non-discrete. What does that mean? That means it's variable, isn't it? For example, let me just draw this for you. Suppose you're listening to music and this is how loud it is, right? You might take the volume on your old amplifier and turn it up where the loudness goes up, doesn't it? You turn it down, it goes down. You see how discrete it is like that? Now the newer, most new ones anyway, they have digital, right? If you're talking about loudness, for example, if you want to turn it up, you have a little, usually they have a little stop. When I say stop, if you take a volume knob and you turn it a little bit, it just clicks to another position and clicks to another position and keeps on clicking all the way around. It never stops. So it might give you a little bit of loudness increase like this. Depending how far you turn it, it's going to go up, right? Could go up even more than one, and then it could start to come down. But you see how each level, it's a discrete value for each level of loudness. It's not a continuous level. We may not hear it because it's so, these steps are so small, but there's your difference basically. This is digital because it's discrete values, and this is continuously variable, right? There are no discrete values. Generally in the physical world we live in, this is the world we live in, analog. We're talking about how loud something is, how bright something is, how hot something is, many other things, how fast we're going. It's always variable, right? Digital, this is the electronics world. This is what all of our equipment is built in usually, and this is how we like it. So a lot of times we have to get from analog to digital, right? That's a story in itself. But I think you have a good idea about basically what it means when we say digital, all right, versus analog. Now, specifically, if we talk about digital here, right, I'll just keep drawing down here. Digital has two values, or two states. I'm going to call it two states. It's either on or it's off. And we could say this is a 0, and that's 0. And by the way, when I draw my zeros, I usually draw a line through them to distinct. They're different than an O. Get it? 0 or a 1. Okay? If you have two states, this is termed as binary. Two states. It's only a 0 or a 1. Okay? Now, if you talk about two logic levels, 0 and 1, we have to talk about their voltages, right? So if we have something like this, and we say this is a logic 0, okay? Now if this is 0, if this is volts over here, and we're at 0.0, I'll make this 0.8 volts. This will be considered a 0. Got it? Now, if we want to talk about a logic high, or a 1, logic 1 or a high, if we come up here and suppose this is plus 2 volts, by the way that's plus here, right? Plus 2 volts, and we come over here, and then up here is plus 5 volts. That's your logic level for a 1, all right, or high. This is your 0 state, or logic 0, between 0 and 0.8 volts. And your logic high, or logic 1, is between 2 volts and 5 volts. Okay? This is important to understand because you're going to be dealing with these logic levels throughout the course. Alright everybody, I'll see you shortly, and we'll start talking about binary versus decimal. See you soon. Alright everybody, so now what I've done here is I've written down the two types of numbering systems that we're going to talk about right now. One type of numbering system you're very used to and you've used probably throughout your academic career here is your decimal, right? So your decimal is base 10, right? So if I write something down, so let me just write a number down. Let me call it 876, okay? Let's really talk about what each one of these means. This digit right here is really 10 to the 0, isn't it? This digit right here is really 10 to the 1. And this digit right here is really 10 to the 2, right? Or you can say this is the 1s, right? You can say this is the 10s, and you can say this digit right here is the hundreds. All right? So what we're saying is we have 6 times 10 to the 0, that digit. We'll add this onto this one right here. We're saying we have 7 times 10 to the 1. In this one, we're going to say we have 8 times 10 to the 2. Or you can say this is 8 times 100 plus 7 times 10 plus 6 times 1. And this would be 800. This would be 70. And this would be 6. You add them together, you get 876. Alright? Now you notice this is base 10. All of these right here are 10 to some number, right? 10 to the 0, 10 to the 1. It all depends how far over you. Alright, so let's try it this way for the binary, okay? Alright, for the binary number, let's try this. Let's write a 1, 1, 0, 1. Okay? What is this saying? Well, this digit right here is 2 to the 0. This digit right here is 2 to the 1. This digit right here is 2 to the 2. And this digit right here is 2 to the 3. Got it? Or in other words, this right here, this digit over here on the right, this is the 1s. This right here is the 2s, right? It's an S, supposed to be an S. This right here is the 4s, and this right here is the 8s, right? So what we're really saying, this is 1 times 2 to the 0. Now this one right here is going to be 1 times 2 to the 1. This one right here is going to be 0 times 2 to the second. And this one right here is going to be 1 times 2 to the third. Or basically, this is going to be a 1 here. This one right here is going to be a 2. This is going to be a 0. And this is going to be an 8. And if you add them together, you're going to get 11. Now, to denote this is decimal here, the number I've written 11 is decimal. I'm going to put a small 10 down here. Same thing I'll do here. That denotes it's in base 10. Obviously, this one is in binary, right? So sometimes you'll see a small 2 here, saying that's denoted in base 2. I mean, if you didn't have that, how would you know if that's not 1011, right? Base 10. Or this could be 11, base 2, right? As I've just shown you, okay? So those are the differences between the numbering systems. That's really what I wanted to show you here. Now, if you think about it, if you have 8 bits, where am I going to put this? Why don't I try it right here in the middle? How's that? I'll just put it right here. If you have 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. All right? Now let's write a number here. 1, 0, 1, 0, 1, 0, 1, 0. All right? You know that this is this is binary, obviously. This is a binary number, so I'm going to put a 2 here in the lowercase, so you know it's binary. Sometimes you'll see the letter B, okay? So this digit right here is the 1's place. I'll just draw a 1 here. This is your 2's. This digit's your 4's. This digit's your 8. This digit here is your 16s. This digit here is your 32. This digit here is your 64. This digit here is your 128. You get it? Remember, this digit here is 2 to the 0. This digit here is 2 to the 1. This digit here is 2 to the 2. This digit right here, that's going to be 2 to the 3rd. This digit right here is going to be 2 to the 4th. You get the idea, right? That's how I came up with these numbers. Now, if you look at this binary number, this digit right here is the smallest. It's 1, right? It's either it's the ones, right? This digit over here on the left is the largest. It's 128, isn't it? So this is known as your least significant bit over here on the right, and on the left this is known as your most significant bit. All right? So you're going to need to know those terms: least significant bit, most significant bit. When you write a binary number, it's always, the least significant bit is always on the right. The most significant bit is always on the left. It does not change. All right? So the reason why I wrote them like this is because the method we use for the base 10 numbering system is identical to the method we use here in the binary numbering system. The only difference is the base. In this case it's base 10, so it's 10 to the 0, 10 to the 1, 10 to the 2. But in binary, it's 2 to the 0, 2 to the 1, 2 to the 2, and so on. But after that, it's simply plugging in the numbers and adding them up. Well, everyone, I hope this has helped you in your understanding of binary versus decimal. And we're going to continue with this very soon. Talk to you shortly. Alright folks, so now let's try a conversion. Let's say we want to go from, let's say we're in decimal, and we want to convert it to binary. Alright? Well, let's try something straightforward right now. Let's look at the number 5, right? How are we going to convert that to binary? Right? How are we going to do this, right? So this is generally the method I use. If we have 5, right? And over here to the right, I'm drawing placeholders for the binary numbers. Okay? So this is base 2. And this is your decimal, base 10, right? So remember, this is your least significant bit right here, and this is the ones, right? That's your least significant bit. And we have 2, 4, 8. You notice how they just double? 16, 32, 64, 128. I just did 8 bits there, right? So we have to go to the point where we have exceeded the value that you're trying to convert your decimal. So 1 is lower, so we keep on moving. 2 is lower, 4 is lower, 8. So we know we're not going to have an 8. This digit and every digit beyond here, this one, this one, this one, this one, they're all going to be zeros, aren't they? Because they're all 1 bit. If we had one of these bits be a 1, for example, suppose this one right here was a 1. That would be 1 times 32, which exceeds 5. So there's no way we're going to have any of these bits be a 1, right? So let me just erase that real quick here. So let's come back here. How many 4s? This is the 4s place. How many 4s will go into 5? Well, I should ask the question, will 4 go into 5? And the answer is yes, it will go in. So I make that a 1. 4. So we'll have 1 left over. Will 2 go into 1? No. Will 1 go into 1? Yes, it will. We'll have one of them. You have a 0. So what you're left with over here on the right is your binary number. Let's say 5 base 10 is equal to 1, 0, 1, 0, 0, 0, 0, 0 in base 2. Now, honestly, sometimes these other digits, it all depends what you're doing. But the problem is if you need to have those upper digits 0. It doesn't hurt anything. Anyway, so by the way, this whole 8 bits, this is called 8-byte. Okay? 4 bits, this is called a nibble. I think I spelled that right. It's a nibble. Got it? But anyway, you can see now we have the binary value right there, right? Let's try another number, shall we? Honestly, what I'm showing you right now just takes a little bit of practice, and very soon you'll get it, and it's going to be like falling off a log, so to speak, right? So let's try another number. Let's just choose, for example, the number 57, okay? There's my 57, base 10, and we're going to write down our binary values. And these are the 1s, 2s, 4, 8, 16, 32, 64, 128. So let's find out where we exceed. Which one of these here exceeds 57? And we can block that one off. So 32 is less than, 64 is greater than 57, right? So that's going to be a 0. And this is going to be a 0, right? So now let's start. Will 32 go into 57? Yes, it will. Leaves 25, doesn't it? Will 16 go into 25? Yes, it will. That leaves 9, doesn't it? Will 8 go into 9? Yes, it will. It leaves 1. Will 4 go into 1? No. Will 2 go into 1? No. Will 1 go into 1? Yes. So there you have it. There's your binary number, right? 1, 0, 0, 1, 1, 1, 0, 0. So when you're writing this equals 57, right? It's base 2 equals 57 base 10. By the way, when you write these, generally you write them in groups of 4, like a credit card, right? So there's a group of 4, then you have a little space, and there you have a group of 4. I mean, it's much easier when you write them in groups of 4 than trying to write one long, huge number without any spaces in it, because it's hard for us humans to not make mistakes, okay? So that's pretty much the method, right? One method for converting it. Let's try another method, shall we? Try another method. By the way, this is called the sum of the powers of 2 method. The other one is going to be called division by 2. So if we look at this, we can take 57, we write it down. 57 base 10, right? Now let's take 57. I'm going to get rid of that 10 there. You understand that's decimal, right? It's definitely not binary, because binary doesn't have the digit 5 or the digit 7 in it, right? So 57 divided by 2. Now what's that going to equal? Well, it's going to equal 26. This is your quotient right here. And we'll just put your remainder right over here, okay? Quotient, remainder. And is it 26? No, that's wrong. This should be actually 28, shouldn't it? Right? And your remainder is going to be what? 1, right? Because 28 times 2 is 56. You have 1 left over, right? Now, let's bring this down. Now we're going to take 28, divide by 2. What's that going to equal? Well, it's going to be 14, and your remainder is going to be 0, isn't it? 2 times 14 equals 28. Let's bring this down here now, guys. 14 divided by 2. What does that equal? It's going to equal 7 with no remainder, right? Seven divided by 2. Quotient, I'm sorry, make that nice and neat. It's going to be 3 with a remainder of 1, isn't it? 3 divided by 2, that's going to be 1 with a remainder of 1, isn't it? Now we have 1 divided by 2, that's going to be 0 with a remainder of 1. Got it? Now, if this value right here there's your binary number, okay? And suppose it was a tree and they have to fall to the right. Let's rewrite it, shall we? So in other words, this is going to be your least significant bit, and this is going to be your most significant bit. So let's rewrite it, starting with the least significant bit. I'll just rewrite it over here. It's going to be 1, 0, 0, 1, 1, 1. Right? Well, let's check our work, shall we? This is the 1s, 2s, 4, 8, 16, 32. Well, let's add them together. 8 and 32 is 40, isn't it? Plus 16 is 56. And then you add this 1 over here, right here, right? That makes 57. There you go. So this is called the divide by 2 method. So you want to know both of them, okay? Honestly, after a while, you'll probably just use the sum of the first method I called you, the powers of 2 method. I think this is used a lot if you're writing a program to do something. This would lend itself to programming quite well. But there are 2 methods for you to convert from decimal to binary. All right? All right, everyone. Now we're going to talk about something called hexadecimal. Talk to you soon. All right, folks. So now I'm going to talk about hexadecimal. Now let's just review for a second. We have decimal, right? That is base 10. We have binary. That's base 2. Now, hexadecimal. Sometimes that is referred to as hex. All right? Let's put dots there. I use that term a lot. That's why I'm letting you know. Instead of saying hexadecimal, I just might say hex. But anyway, hex or hexadecimal, base 16. All right? Now don't fall over in your chair or anything. All right? This is just this is the last numbering system you're going to be introduced to here in this course. All right? So 10, base 10 you already know. 2, binary, you know now. So we just got one more to go over, right? So let's just write these down, shall we? Let's write down hex. And let's write down decimal. Come on, man. There we go. And then we have binary. B-I-N-A-R-Y, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Actually, I made a mistake, didn't I? Did you catch it? We don't start at 1. We start at 0, don't we? Now, decimal 0, hex is 0. That's equal to decimal 0, right? Binary, it's equal to what? By the way, this binary number in this column is just going to be 4 bits. Okay, it's going to be a nibble long. 1 in hex is equal to 1 in decimal, which is equal to, that's 1 in binary, right? 2 in hex is equal to 2 in decimal. This is going to be equal to 2 in binary. 3 in hex is equal to 3 in decimal, which is going to be equal to 3 in binary. You can see that, right? We're just counting down. 4 in hex is equal to 4 in decimal, which is going to be equal to 4. Now, I could keep on writing these down over here in binary. I'm just going to point you down here. I'll do it at the end. All right, I think you guys get the idea. Okay. Now, 4 goes to 4, 5 goes to 5, it maps to 5, 6, 7, 8, 9. Now listen, now we've run out of digits, haven't we? So if we're in the decimal numbering system, we start a new placeholder, right? So then we go to 10 is 11, 12, 13, 14, 15. Got it? There are 16 numbers here, 0 through 15. Get it? But hexadecimal, we have to go all using one digit. We have to go count all the way to 15. So instead, we just start using the alphabet. The capital letter A maps to decimal 10. Capital letter B maps to letter 11. Capital letter C maps to 12. Capital letter D, 13, E, 14, F, 15. Let's see this. A, B, C, D, E, F. There you go. Now if we're bringing the binary down here, right? Let's keep bringing let's say we're at 10 here, right? Let's just bring 10 over here. Well, what's that going to be? That's going to be 0, 1, 0, 1, isn't it? 11 is going to be 1, 1, 0, 1. All right. What's the next one? 12, isn't it? That's going to be 0, 0, 1, 1. 13, 1, 0, 1, 1. 14, 0, 1, 1, 1. And 15 is going to be 1, 1, 1, 1. So 15 hexadecimal is all. So 15 hexadecimal is all ones, binary for that nibble. All right. So there you have an explanation of what hexadecimal is. Now, by the way, it's the exact same method as we did before, as we used before. If I write 1, 1 base 10, this is 10 to the 0. This here is 10 to the 1, right? So we have 1 times 10 to the 1 plus 1 times 10 to the 0. And that's equal to 11 base 10, right? Obviously. So let's do this here now. Let's write 11 in binary. You notice how I wrote a B instead of a 2? It means the same thing. Well, this digit is what? This is equal to 2 to the 0. This digit's equal to what? 2 to the 1. So this is equal to 1 times 2 to the 1 plus 1 times 2 to the 0. Got it? And so this would be equal to, what would that be equal to? 3 in decimal, base 10, right? All right, now let's continue. One base 16, or I could write this down as 1 hex, couldn't I? This is this digit right here is equal 16 to the 0, and this digit right here is equal to 16 to the 1, isn't it? So this is right here is equal to 1 times 16 to the 0. And this one right here is equal to 1 times 16 to the 1. We're adding them together. So this is going to be 16 plus 1 is equal to 17 in decimal, or base 10, right? What if this was, let me see what I'm going to do. I'm going to try this one. What if that was an A? 1A hex. Let's talk about that, shall we? What's 1A hex going to be? So this, if we look over here, A is equal to 10, right? So this is going to be 10 times 16 to the 0. And this will still be 1 times 16 to the 1. So what's this going to be? It's going to be 10. Right? 16 to the 1 is 1, so it's just going to be 10 times 1, which is 10, plus 1 times 16 to the 1. 16 to the 1 is just 16, so it's just going to be 16. This is going to equal to 26 base 10, right? Let's try something else, shall we? Let's just choose, suppose this is AA, just for the heck of it. Why not? AA. In hex, what is that equal to? Well, we already know this side, right? This is going to be 10. Because A is equal to 10, right? Here it is. A is equal to 10 right there. Okay, A is equal to 10 in decimal. So it's going to be 10 times 16 to the 0 plus 10 times 16 to the 1. Well, 10 times 16 to the 0, that's 10. 16 to the 0 is 1, so this is equal to 10. Well, 16 to the 1 is equal to 16 times 10, that's equal to 160. And you put them together, you get what? 170. You see it? That's pretty much how it's used. So let's try counting, shall we? Again, the method is identical. This is base 16. We use base 10 in most of our normal day-to-day lives. Binary, base 2 we talked about. You could have a numbering system with any base you want. You could have a base 7, you could have a base 9. Don't know why you would want to have those, but you could have them in any way you want, right? So let's try this here, shall we? Let's try to count for a minute. So let's say we want to count. Let's try this. We're in hex, right? Hex. Sometimes you see it like this with a big H to the right. That means you're in a hex. So you've seen all three types of notations. So in literature, when you're reading, you could see any of them, right? So what's next? If we want to count that, what comes after this one? It's going to be 1A, right? After that, 1B, 1C, 1D, 1E, 1F. Now what comes after 1F? Well, we're at F, right? It has to recycle back. Let me just draw this for you. It has to recycle, doesn't it? So then one after this was going to be 0, isn't it? And the decimal is going to have to increase. I'm sorry, I said the decimal, that doesn't make sense. I'm talking about this column right here, the 16 to the 1s column will increase, so that's equal to 20. By the way, 20 hex, what's that equal to? Okay, if you said 32, you're right, because this right here, that's equal to 2 times 16 to the 1. Which is equal to 2 times 16, which is equal to 32. Get it? So that is really what hexadecimal is, all right? Let's talk about conversions, shall we? If you're going to convert something to decimal, hex to decimal we've already done, so you know how to convert from hex. You know how to go from hexadecimal to decimal. We just did that, right? So that shouldn't be a problem, okay? Now, if you're going from decimal to hexadecimal, this is how I would suggest you do it. I would suggest you convert your decimal take your decimal, convert it to binary, and then from binary convert it to hex. So when you convert your decimal to binary, which you already know how to do, and you write it in groups of 4 starting from your least significant bit, you're going to have these numbers right here, right, all the way down. And then it's a simple matter then to convert these values here, in these values in this column, to your hexadecimals values in this column. All right, so I can't remember what 57 was. Let's try that, shall we? If we want to go 57 decimal, we want to find that what it is in hexadecimal equals hex, right? Well, first let's take 57 and convert it, right? So 57, let me just get some room here. Let's just do this, shall we? $57. Okay, you want to do the divide by 2's or the sum of the powers of 2's method? You can do that pretty quick, right? What do we have? We have 1, 2, 4, 8, 16, 32, 64, and 128, right? So we know 128 is 0, we know 64 is a 0, right? 32 will go in there. So we have 32. If we subtract it, we have 25. We know 16 will go into 25. That leaves a 9. 8 will go into 9, right? Leaves 1. Well, 4 can't go into 1. 2 can't go into 1. 1 will go into 1, right? 0. So there we have it. Now look. Let's just take these. Let's just rewrite this, shall we? It's 1, 0, 0, 1 space 1, 1, 0, 0. Okay? Well, what's 1, 0, 0, 1? Do we have it here? That's going to be, actually I don't think I wrote that down for you. If we wanted to write it down, it's going to be right there. It'll be right there. It's a 9, okay? So this is equal to 9 hexadecimal, which is right here. Got it? Now what's this one equal to? What's the one to the left of it equal to? That's 1, 1, 0, 0. Ooh, look at it right here, right? Over here, I don't know if it lined up quite right. That's 3, isn't it? So this one here is equal to 3. So it's equal to 39 hex. Got it? So this is what I recommend. You follow this trail. Go from decimal, go to binary, and from binary to hex. Alright, it's less confusing that way. Eventually you'll be able to go use, you won't have to do that. You can go from hexadecimal right, decimal right to hexadecimal, or vice versa, but it takes practice. I think going to binary first will help you. All right, everyone. I think that will end our discussion on hexadecimal. We have one more quick topic to talk about, and that's waveforms. See you soon. So let's talk about waveforms in timing diagrams, shall we? So first thing is, if we have a signal, let's just draw a signal. We draw this, so here's a time. Time is on our x-axis, which I'm drawing tick marks on. And the farther right you go, the more time has passed. Okay? So I'll just draw a big old T there for time, shall we? Now on this axis, let's just say it's either a 0 or a 1. Okay? Now, let me change colors here to blue. Suppose you have a pulse like this. It comes along here, it's 0, 0, and then it jumps up to 1, comes back down. And then it's 1, 2, 3, does another 3, 0, and it just repeats this. All right? Now, this is an example of a periodic digital waveform. Periodic means it repeats. It's regular. You know what's going to happen in the future on this, right? So, if these were now times, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you notice, usually you look at these from one pulse to the next. One way to look at it is the rising side of the pulse. This is one cycle. The rising side of the pulse gives the period or the time between the pulses. Now, we could have just as easily said that's one cycle right there from 3 to 7, right? Obviously, every 4 cycles, or I'm sorry, every 4 units of time, if this was milliseconds, we'd call it milliseconds. Every 4 milliseconds, right? 1, 2, 3, 4, it repeats, right? But guess what? This could also be done this way, couldn't it? We could look at it right here. Again, one cycle, but guess what? It's the same period, isn't it? This is when it's actually, this is the rising edge here. It's rising. So at this edge, the right edge of this pulse to the right edge of the repeating pulse, you're looking at the waveform slightly differently, but the cycle remains the same. It's still 4 units of time for it to repeat. You get it? So now, let's try this. Let's try this, shall we? If we're going to look at it, let's say from here to here. That's one cycle. Okay? And then the same thing here. Here, here, that's one cycle, right? what I just drew you, this whole thing right here, the entire, this is a timing diagram. Alright? It gives the pulses, it gives the time, it's going to give you units here. It could be in milliseconds or microseconds, depending what these values are. But you'll be able to see a pulse. Now, many of you may have not used this, but there's a tool in the lab called an oscilloscope, and this is what you're going to see on it. Alright, you see basically a timing diagram. It's very useful. Alright. Now, some timing diagrams you're also going to have another pulse, another waveform right below it, and you could have another waveform right below that as well. But let's just make it simple right now, and let's just say that's what we're looking at. Okay. Now, I want to talk to you about some definitions right now. Okay. So, if we look at the time high, okay. T stands for time, right? So we're going to say time high. Right here is the time it's high, right? Okay? If we look for time low, that's obviously the time it is low, right? Now, let's talk about the period. Capital T, that represents the period. That is in units of time. Units of time. Got it? So basically that is the time of one cycle. Okay? So it's the time required for this waveform, a periodic waveform, to repeat. So I'll just write down over here time for one cycle. Got it? Okay. Now, there's also something called frequency. Frequency, sometimes you'll just see a capital F. Now, sometimes you're going to see this. It's a lowercase f, but a big lowercase f. And sometimes you'll see it like this in the literature. Like that. They can draw it many different ways. But that is basically equal to 1 over your period. Right? So this is going, the units are going to be, this is important to understand this, 1 over time. So usually this is referred to as cycles per second. Okay? And this is also called hertz. Units of hertz are cycles per second. Okay? So hertz equals cycles per second. Alright? Got that? Now, let's continue here. We have more things to discuss. This is going to be a very useful discussion for everyone here. The next thing, we have frequency, period. Let's talk about duty cycle. I'm going to just continue over here. I'll draw a little line over here. That's equal to the time high, okay, the amount of time high divided by the period t. Alright? Now, this is usually multiplied times 100%. Okay, because usually this is in percent, but you know, time high is in, say, seconds, for example. The period's going to be in units of times. Say it's in seconds, right? So these are going to cancel each other out, so it's unitless. That's why you multiply it by percent. But if you look up here at this right here, you notice that there's 4 units of time for each cycle. In one cycle, it's high, isn't it? So if it's high for one cycle, in the period it takes 4, I'm sorry, I shouldn't use the term cycle, that's a wrong term, I shouldn't say cycle. It's high for 1 unit of time, and there are 4 units of time in one cycle. It's going to be 1 unit high divided by 4 units for a complete cycle times 100%. That's going to give you a 25% duty cycle. Alright? I want to make sure everyone understands that. Okay? Time high, that's the amount of time it's high per cycle. Time low, that's the amount of time it's low per cycle. The period, that's the total time for one cycle. Frequency, that's going to be 1 over your period. The units are going to be 1 over time, which are equal to hertz, and hertz is equal to cycles per second. Alright? And finally, the duty cycle. The duty cycle is defined as the time high divided by the period times 100%. And so in the example which I drew up here, okay, it's high for one time period from 3 to 4, and the period is equal to 4, right? Because you have 1, 2, 3, 4 time periods per cycle. So that's where you get each one of these numbers, and 1 divided by 4 is 0.25. 0.25 times 100% is equal to 25%. Alright? So that should help you understand timing diagrams and basic terminology and how to figure it out for this class. Now, there are something called aperiodic waveforms. Okay? Aperiodic waveforms are not regular. I'll make that 1 and 0 again, alright? And I'm going to draw an aperiodic waveform right under here for you, just to make sure you understand it. So an aperiodic waveform, I draw it like this. And let's have 1 here and 0 here. And we're going to draw these timing diagrams just like I did before. You might want to do this in your notebook while you're watching this video. It may help you. Remember, right? Now, let's draw a pulse. Suppose you have a pulse here. And then it comes here for 1, and it goes up 1. And then it comes here, stays low for, say, 3, and then comes up here. You know, I didn't continue this across enough. I'm sorry. This would be 10, and then we'd have 11 over here, units of time. The point I'm trying to make is it's not regular. Okay? This waveform does not repeat. It's irregular. So when you have an irregular, right, or an aperiodic waveform, That's much different than a periodic waveform. With an aperiodic waveform, you can't you can't calculate duty cycle. Well, no, because there's no cycle. You can't calculate frequency, period, anything like that. All right. So that's the difference between them. Okay. Finally, let's talk about a pulse. All right. So if I look at a pulse in this format, let's say we have 1 here and 0 here. I just zoomed in is what I did, okay? Now suppose you have a pulse that goes up here. What did we say? So for a positive going pulse, this is the falling edge. And this is the rising edge. All right? So on a negative going pulse, it's the opposite, but let's stick with the positive going pulse here. All right? So it rises and then it falls. Remember how an oscilloscope works, it has a, you may not have seen one, but it has a little dot that goes up, comes down, similar to a, if you think of looking at someone's heart on a monitor. So remember, it's traveling this way, it's going to bump up, that's the rising edge, boom, boom, then it's going to come down, and that's your falling edge. All right. Now, this is important to remember when you're looking at pulses and trying to understand how how to characterize them. Okay. Finally, this right here, between here and here. Okay, this is your pulse width. All right. Now, if you have strange looking pulses, sometimes they want you to measure this at a specific amplitude. For example, they might want you to measure it right here in the middle. They might want you to measure it at 90%, which is very close to the top. They may want you to measure it down here. When I say they, it depends on what you're doing and how you're supposed to measure it. So if someone asks you to measure a pulse width, you need to inquire, well, where would you like me to measure it? Because that can make a difference. Because pulses are not always regular and square. They could, for example, look like this. And as you can see, you have some distance here that you have to account for depending where you're going to measure it. All right? All right, everyone. I think that will conclude our discussion on pulses. I hope this has helped you, and I will see you soon. Thank you.